So picture this. You're cruising down the highway, right?
Okay, I'm picturing it.
You are in this like high performance dual motor electric vehicle. The weather is gorgeous. You're holding steady at I don't know, maybe 80 miles per hour.
Sounds pretty ideal.
It is. The dynamic handling feels perfectly dialed in. You're just relaxing. But then literally without any warning, the car just violently jerks.
Oh, wow. Yeah, that's terrifying.
Right. Or, maybe it just completely loses all thrust. Or, and this is the absolute nightmare scenario, it accelerates completely out of your control.
Yeah, that is the ultimate fear for any driver.
Totally. And like your immediate instinct as a driver is probably mechanical, right? You assume, I don't know, a tie rod snapped or maybe a half shaft just sheared right off the differential.
Of course, yeah, because you feel a physical jolt. You expect a physical break.
Exactly. But the nightmare scenario we are unpacking today for this deep dive, it isn't a mechanical fracture at all. The actual culprit is a microscopic disruption.
Right, a totally invisible glitch.
Yeah. It's a failure of the vehicle's control architecture to know exactly where the spinning rotor of the electric motor is. And we're talking about losing track for just a fraction of a millisecond.
Which is wild. I mean, it is basically the defining nightmare of modern functional safety.
It really is.
And, to understand exactly how deep this rabbit hole goes, we really need to look at the materials you provided for us today.
Oh, yeah, it's intense.
It is. We are analyzing a deeply technical, I mean really dense, 47-page engineering masterclass.
Yeah.
And it's focused specifically on, let me get the title right, dual motor PCS controller rotor position, estimation failure analysis, and prevention strategy.
Which is a mouthful, but man, in that stack of automotive forensics you sent over, they do not mince words.
No, they don't. They treat it with the gravity it deserves.
They really do. They classified this specific failure as an ASIL-D hazard.
Right, ASIL-D.
And for anyone diving into this research along with us, ASIL-D represents like the absolute highest risk classification under the ISO 26262 standard.
Which basically means there's no room for error.
0. We are talking about failures with an immediate potential for catastrophic, life-threatening events. But what really stood out to me in the documentation you shared is the FTTI.
Ah, yeah, the fault-tolerant time interval.
Right.
The FTTI parameter is where the engineering reality becomes just brutally unforgiving. I mean, for a rotor position estimation failure in a high-voltage dual motor setup, the mandated FTTI is strictly less than 60 milliseconds.
Okay, wait. I want to frame that 60 millisecond window for you because it sounds fast, but it's hard to visualize.
It's basically the blink of an eye.
Faster even. Look, if you are traveling at 80 miles per hour, your car is covering roughly 117 feet every single second.
Right.
So in 60 milliseconds, you travel just about 7 feet.
Wow, 7 feet.
Yeah, that means the car's dual-core processors have exactly 7 feet of physical tarmac to, detect an impossible mathematical anomaly.
Verify that it isn't just, a random sensor noise spike.
Exactly. And then execute a torque abort command and physically clamp down the high-voltage switches, all in 7 feet.
And if the system takes, say, 65 milliseconds instead?
Then the magnetic field vectors misalign,
Hi.
the inverter dumps maximum current into the wrong phase, and the vehicle physically destabilizes.
So the margin for error is effectively 0.
Literally 0. And our mission today is to decode how engineers hunt down these sub-millisecond failures that often leave almost 0 visible trace.
It's basically high-tech detective work.
It really is. So we are going to examine the 4-dimensional forensic methodology they use to autopsy these systems.
Right, starting from the physical evidence.
Yeah. And from there, we'll unpack 16 distinct root causes, which range from, high-frequency parasitics to literal single-event upsets caused by cosmic radiation.
The cosmic radiation part is just mind-blowing.
I know, we will definitely get to that. And finally, we'll explore the 6-dimensional defense architecture and the 8D operational framework required to prevent these anomalies on a massive industrial scale.
It's a huge journey. Where do we even start?
Let's start with the forensics. When a dual-motor power control system, or PCS, fails on the highway, the physical evidence is usually microscopic.
Right. You're not finding a giant cracked gear.
Exactly. The source material outlines this really cool 4-dimensional closed-loop analysis method. And the first dimension is macroanalysis, which is basically the visual autopsy.
Okay, so what are they looking for with the naked eye?
Well, they're looking for obvious thermal ablation on the high-voltage bus bars or maybe heavy oxidation patches on the connector pins. But the document highlights a specific mechanical artifact that just blew my mind.
Oh, the fluting.
Yes,
Yeah.
fluting on the motor bearings.
Fluting is such a fascinating diagnostic indicator because when investigators pull the steel bearings from the motor shaft, they often find this distinct, highly regular washboard-like wave pattern.
Literally physically scarred right into the metal raceway.
Exactly. It looks exactly like microscopic corrugated metal. Now, mechanical engineers might initially misdiagnose this, right? They might think it's just simple vibrational chatter or maybe improper bearing preload.
Because it looks mechanical.
Right. But electrical engineers recognize fluting as the physical signature of severe electromagnetic violence.
Electromagnetic violence. I love that term. And that makes sense because if you transition to the second dimension of the investigation, in the microanalysis, you start seeing exactly how that violence actually occurs.
You zoom way, way in.
Yeah, the engineers don't just rely on like 10x magnification. They put these components under scanning electron microscopes paired with energy dispersive X-ray spectroscopy, or EDX.
The EDX analysis is critical here. It's amazing technology.
Yeah.
Basically, an electron beam strikes the sample, right?
Okay.
And it ejects inner shell electrons from the atoms on the surface.
Okay.
When outer shell electrons drop down to fill those vacancies, they emit X-ray photons. And here's the key. Every element on the periodic table emits a uniquely identifiable X-ray energy signature.
So it's like a fingerprint for the exact chemical makeup of the surface.
Exactly.
And if you're looking at page 12 of the research you sent us, they use this EDX process to hunt for something highly specific. They look for localized spikes in oxygen concentration.
Right, along sliding tracks on the terminal pins.
Sliding tracks that are only like 1 to 200 microns wide. And if you think about it, finding a massive oxygen spike inside an IP67 rated hermetically sealed electrical connector, that proves you don't have a broad environmental water leak.
No, you have a highly localized tribological failure.
Right.
Precisely. That oxygen spike basically confirms that the protective noble metal plating has been physically sheared off by microscopic vibration.
Just rubbed right off.
Yeah, and that exposes the base copper alloy to whatever trace atmospheric oxygen is trapped inside the housing.
And then it rusts, basically.
Well, the resulting oxidation forms an insulating layer, which fundamentally alters the contact resistance. We will get into the catastrophic chain reaction that causes shortly, but the microanalysis goes even deeper than surface chemistry.
Oh, it gets crazier. They utilize scanning acoustic microscopy, or SAM, to inspect the internal structure of the analog front-end components.
SAM is incredible. It is essentially an ultrasonic phase array for microchips.
Yeah, using literal sound waves. Piezoelectric transducers fire ultra-high frequency sound waves directly into a solid ceramic capacitor.
And you have to use acoustic waves because the failure mode they're looking for is entirely invisible to an electron microscope. It's divisible to a standard X-ray.
So what are they listening for then?
They are hunting for acoustic impedance mismatches. See, when the sound wave travels through the uniform ceramic matrix, it propagates predictably. But if there is a microscopic delamination,
Like a tiny crack.
yeah, a void or a stress fracture just a few nanometers wide, hidden deep inside the solid capacitor, if that's there, the acoustic wave reflects back differently.
That is so cool. It allows the forensic team to prove that a component was internally compromised before the thermal event even happened.
Exactly. So they know the fracture caused the fire, rather than the fire causing the fracture.
Okay, so that brings us to the third dimension, which is material analysis. This is where the investigation shifts toward, like, supply chain validation.
Catching suppliers who cut corners.
Exactly. The lab deploys X-ray fluorescence, or XRF, to verify the exact thickness of the terminal plating.
Right, because the engineering specification for the soft gold plating on these specific resolver terminals is strictly set at a minimum of 1.27 microns.
1.27 microns. That is impossibly thin.
It is. But if the XRS spectrometer reads, say, 1.1 microns, that batch is flagged as the root cause.
Just because it was missing a fraction of a micron of gold?
Yeah, because the material science dictates that anything less than 1.27 microns lacks the required ductility to survive the high-frequency modal vibrations of a dual-motor chassis.
Wow. And the documentation also highlights positive material identification PMI, which is used on the high-voltage busbar fasteners.
Right, the bolts holding the heavy copper bars together.
They are checking for the presence of a phosphate conversion coating. I mean, it just seems insane to me that missing a microscopic chemical dip on a single steel bolt can result in an acyl D highway failure.
I know, it seems extreme until you reach the fourth dimension of the investigation. Data math.
Ah, the digital confession?
Exactly. This is where the engineers correlate all that physical evidence,
Yeah.
the fluting, the oxidation, the missing phosphate, with the vehicle's high-speed telemetry.
Right. And in a silicon carbide, or 6 inverter, the power modules are switching immense amounts of current. The voltage transition rate, the DVDT, is an aggressive 10,000 volts per microsecond.
Just think about that. A 10,000-volt transient happening in a millionth of a second.
Yeah.
The physics there are terrifying.
Really terrifying. And when you plug that DVDT value into the formula for current through a capacitor, which is, current equals capacitance times the derivative of voltage over time, or I equals C times dVdt, the implications become really clear.
Because of parasitic capacitance.
Exactly. Even a tiny, completely unintended parasitic capacitance of just a few picofarads between two adjacent wires will inject a massive spike of noise current directly into the delicate analog sensor lines.
Precisely. And so the data math dimension takes those parasitic coupling models and it aligns them with the thermal cycle logs, which range from, minus 40 to plus 150 degrees Celsius?
Yeah, extreme temperatures.
And then they cross-reference all of that against the exact timestamp of the loss of track, or LRT fault codes.
So basically what you're saying is this is literally a forensic crime scene investigation.
Completely.
You've got the medical examiner doing the autopsy, but instead of just looking at the trauma, they're using x-rays and complex math to prove the supplier cut corners on the microscopic coating of a single bolt, and that caused the crash.
Exactly. They aren't just guessing what happened. They are mathematically proving that the physical material failure and the electromagnetic transients intersected at the precise millisecond the processor lost its angle estimation.
Man. That perfectly transitions us into section 2 of your materials, the hardware saboteur.
The physical realities of the automotive environment.
Right. We now understand the forensic tools, so what exactly are these tools uncovering? The document lists 16 distinct root causes. And honestly, the physical environment of an EV powertrain is easily one of the most hostile environments for delicate silicon.
Absolutely brutal.
So let's look at that 10,000 volt per microsecond switching speed again. The first failure mode they list is high-frequency electromagnetic interference. Specifically, it's driven by a wiring shortcut known as the pigtail ground.
Yeah, the pigtail. So in lower voltage systems, taking the braided metal shield of a sensor cable, twisting it into a single wire, which is the pigtail, and bolting it to the chassis ground is pretty standard practice.
Because it provides a simple DC path to ground, right?
Exactly. But at high frequencies, a pigtail is a severe liability.
Because at those switching speeds, you aren't dealing with simple DC resistance anymore. You are fighting parasitic inductance.
Precisely. A twisted wire has inherent inductance. When that aggressive 10,000 volts per microsecond common mode noise hits the shield, the inductance of that pigtail creates a high impedance bottleneck.
Basically, the noise current just cannot flow to ground fast enough.
Right. Consequently, the voltage on the entire shield spikes. The shield effectively ceases to be a Faraday cage and becomes an actively radiating antenna.
Oh, wow. So instead of blocking the noise, it's broadcasting it.
Exactly. It capacitively couples that high-frequency noise directly into the internal resolver signal wires. And then the analog-to-digital converter sees this noise, misinterprets the voltage levels, and calculates a wildly erratic rotor angle.
So the system is perfectly healthy physically, but the noise fundamentally corrupts the observation.
Yes, it's blinding the sensors.
That is wild. Okay, so the next physical saboteur involves those capacitors we were scanning with acoustic waves earlier, thermal drift. The documentation points out that substituting a stable capacitor with a cheap Class 2 X7R ceramic capacitor in the analog front end is a catastrophic error.
Yeah, to understand why, you really have to look at the dielectric material. Class 2 X7R capacitors use a barium titanate crystalline structure.
Okay, barium titanate.
And barium titanate is ferroelectric, meaning its internal electric dipoles are highly sensitive to both applied voltage and extreme temperatures. So when the inverter compartment reaches, say, 125 degrees Celsius, the crystal lattice physically expands.
And when it expands, the dielectric constant just plummets.
Exactly.
The research you provided states that the capacitance can drift by over 15% at the temperature extremes.
Which is huge in this context.
Right. If the resolver's differential signal pairs rely on perfectly symmetrical filtering, a 15% drift on one side completely destroys the common mode rejection ratio. The signal amplitude collapses below the 2.3-volt peak-to-peak threshold required by the resolver to digital chip.
And that triggers an instantaneous hardware lock loss.
Wait, so let me get this straight. A capacitor getting a little too hot can blind the entire car to what the motor is doing.
Yeah, pretty much.
It's like trying to navigate a ship by the stars, but the glass in your telescope physically warps every time the weather gets warm.
That is exactly what happens. The signal conditioning circuit basically goes blind purely because the molecular structure of the capacitor shifted in the heat.
That is so fragile. Okay, let's circle back to the EDM craters. The electrical discharge machining causing the fluted bearings we discussed in the visual autopsy. How does a literal steel bearing become a spark gap?
It comes back to the parasitic capacitance of the motor architecture itself. The rapidly switching stator windings capacitively couple to the rotor iron, which induces a high-frequency common mode voltage on the spinning motor shaft.
Okay, so the shaft gets electrified.
Right. Now, the shaft rests on steel bearings, but it is floating on a microscopic hydrodynamic film of lubricating oil.
And oil is an excellent dielectric. It's an insulator.
It is. Up to a point, we measure shaft voltages hitting anywhere from 70 to 370 volts. And depending on the exact thickness of that oil film at any given RPM, the electric field strength eventually exceeds the dielectric breakdown voltage of the lubricant.
And when that happens?
When that happens, you get a Townsend avalanche.
A microscopic lightning strike tearing straight through the oil.
Exactly. An ionized plasma channel forms, and the built-up charge arcs violently from the inner raceway right through the plasma to the outer raceway.
Wow.
And the localized temperature of that microarc vaporizes a tiny pit into the hardened steel. At 15,000 RPM, this electrical discharge machining is happening thousands of times a second.
So it's just blast after blast.
Yeah, it physically excavates the bearing metal, causing that corrugated fluting pattern we talked about.
And as the bearing geometry degrades, the rotor is naturally pushed eccentrically off-center. And an eccentric rotor warps the air gap between the stator and the rotor.
Which introduces spatial harmonics into the magnetic field.
Right. Which fundamentally distorts the resolver's angle reading. It is just a stunning cascade. Electrical noise causes physical machining, which causes magnetic distortion, resulting in a software failure.
It's all connected. Which brings us to the next tribological nightmare on the list. Fretting wear and micro-arcing at the connectors.
Right, going back to the EDX, finding oxygen spikes inside the sealed housing.
Yeah. A high-performance vehicle chassis experiences intense modal frequencies. This high-frequency vibration forces the mating surfaces of the electrical pins to slide against each other.
But only by like 1 to 200 microns, right?
Exactly. It is an almost imperceptible movement. But over millions of cycles, the shear forces at the microscopic asperities, the tiny peaks and valleys of the metal surface, tear the protective gold plating completely off.
Once the base metal is exposed and it oxidizes, the contact resistance skyrockets. We're talking going from a nominal 5 milliamps to well over 100 milliamps.
And that's where the real danger starts.
Because when you try to push sensor current through that highly resistive barrier, the voltage bridges the microscopic gaps created by the wear debris. You basically generate a sustained microarc.
Yep, and the temperature of that plasma arc easily carbonizes the surrounding thermoplastic connector housing into a conductive ash.
Which instantly shorts the resolver signals together. It is an irreversible hardware destruction triggered by a 100-micron vibration.
A vibration you wouldn't even feel in the cabin.
Unbelievable. Okay, what about the missing phosphate coating on the busbar bolts? This ties back to the PMI testing. How does a microscopic surface treatment dictate torque?
Well, it dictates the relationship between torque and clamping force, and those two are not the same thing.
Okay, break that down for me.
So the torque applied by the factory automated screwdrivers is governed by a specific equation. Torque equals the K-factor times the nominal diameter times the target clamping force.
And the K-factor represents the friction coefficient of the threads.
Right. The phosphate coating basically acts as a dry film lubricant, providing a very specific low K-factor.
But if a supplier skips the coating to save a few pennies,
then the raw steel-on-steel friction completely spikes the K-factor. The servo screwdriver applies a programmed torque, but the vast majority of that rotational energy is wasted just overcoming the thread friction.
So the tool registers a successful torque operation because it hit the number, but the actual clamping force pressing the copper bus bars together is dangerously low.
Exactly. And under heavy acceleration, hundreds of amps are flowing through that inadequate joint. The reduced contact area means high electrical resistance.
Which triggers I squared R thermal runaway.
Yeah, the joint generates massive heat, which increases the resistance further, which generates even more heat until the bus bar physically melts and severs the phase connection.
All because they missed a chemical dip on a single bolt. The physical saboteurs in these systems are just relentless.
They really are.
But moving into Section 3 of your provided research, we encounter a completely different class of failure modes. We leave the realm of mechanical friction and parasitic inductance entirely and enter the realm of pure data corruption.
The ghost in the machine.
The ghost in the machine. And honestly, the first software failure mode on this list sounds like actual science fiction.
Cosmic rays causing single event upsets, or SERs.
It sounds like a movie plot.
Right.
But in sub-20 nanometer silicon architectures, it is a deeply mathematical reality.
It is. At the subatomic level, the Earth is constantly bombarded by high-energy particles. We're talking cosmic rays from the atmosphere, and even alpha particles emitted by the radioactive decay of trace uranium or thorium impurities.
Impurities that are present in the black plastic mold compound of the microchip packaging itself.
Exactly.
Wait, I really want to emphasize this. The chip's own plastic packaging is shooting alpha particles into the silicon die.
Yeah, it's essentially irradiating itself from the inside.
That is wild.
And when an alpha particle strikes the sensitive depletion region of a static RAM cell and SRAM cell inside the microcontroller, it generates a microscopic track of electron-hole pairs.
And if the charge collected by the circuit node exceeds the critical charge threshold of that specific transistor,
It forcibly changes the voltage state.
it physically flips a digital 0 into a digital 1, a literal bit flip.
Without any software command or logical reason whatsoever.
So if that specific SRAM cell was holding the most significant bit of the calculated rotor angle, the processor suddenly reads that the motor has instantaneously teleported 180 degrees.
Exactly. The data is poisoned at the quantum level.
It's wild to me that a literal subatomic particle from deep space could cause a car to brake on the highway.
It's the reality of modern electronics.
Yeah.
But, the chips can also poison their own data through timing errors.
Right. The research highlights clock metastability as a primary failure mode when coordinating the main microcontroller, the MCU, and the resolver-to-digital converter, the RDC.
Yeah, because digital logic relies on strict timing parameters.
Yeah.
Setup time and hold time. Think of the clock signal as a rigid square wave that dictates exactly when data can be safely sampled.
Okay.
If the MCU and the RDC are running on separate internal clock oscillators, their frequencies will inevitably drift due to temperature gradients across the circuit board.
One part of the board gets hotter than the other, and they lose synchronization.
Exactly. And if the MCU attempts to read the angular data bus from the RDC at the exact picosecond, the RDC is transitioning its output from a low voltage to a high voltage.
The MCU's input flip-flop samples an intermediate, totally invalid voltage level.
Right. That violation of the setup and hold times triggers metastability.
Yeah.
The internal transistors of the flip-flop literally cannot resolve whether the signal is a logical one or a zero.
So it just panics?
The output hovers in a metastable state for an unpredictable amount of time before it finally collapses randomly. So the MCU ingests completely randomized garbage data.
And it interprets that garbage as wild, instantaneous fluctuations in the rotor position.
Exactly.
That brings up a fascinating architectural challenge specific to these dual-motor PCS units, which is spatial crosstalk, because you are packaging two incredibly high-power inverters into a single, compact aluminum housing just to save weight and volume.
The spatial density is a massive engineering trade-off. Motor A and motor B are electrically independent, obviously, but they share the exact same physical cavity.
Right.
So when motor A executes, say, a launch control acceleration, the massive rate of change of current, the DIT, generates an intense, localized, near-field magnetic footprint.
And going back to Faraday's law of induction, that expanding and collapsing magnetic field will induce unwanted voltages into any adjacent conductive loops.
Precisely. If the delicate analog sensor traces from motor B happen to route too closely to motor A's power stage, motor A will inductively couple its switching noise directly into motor B's telemetry.
That is crazy. So motor B could be completely stationary, yet its processor will read intense, erratic movement purely due to near-field magnetic crosstalk from the motor next to it.
Yeah. It requires extreme spatial discipline in the PCB layout to prevent the inverters from essentially blinding each other.
Wow. Now, when the primary hardware sensor does fail, whether it's from crosstalk, an alpha particle, or a severed wire, these ASOL-D systems utilize a software backup called sensorless control.
Right. Which relies on a sliding mode observer or SMO algorithm.
Right, since it doesn't have a physical resolver anymore. The software mathematically estimates the rotor angle, by analyzing the back electromotive force, or back EMF, that's being generated by the spinning motor.
That is the core mechanism, yeah.
Yeah.
The back EMF is directly proportional to the rotor's speed and position. However, the software cannot measure back EMF directly while it is simultaneously driving voltage into the motor.
So it has to calculate it.
Exactly. It uses a complex matrix equation that relies heavily on a fixed parameter, the physical resistance of the copper stator windings.
But the resistance of copper is not a fixed parameter at all. It has a positive temperature coefficient.
Yeah, very much so.
As the motor runs hard and the internal temperature climbs from, say, 20 degrees to 130 degrees Celsius, the physical electrical resistance of that stator winding increases by roughly 40 to 50%.
And that introduces sensorless control divergence.
Because the math is wrong now.
Right. If the SMO mathematical model assumes the stator resistance is still 20 milliamps, but the physical reality is 30 milliamps, the internal state observer subtracts the wrong voltage drop from his calculations.
The matrix diverges.
The calculated angle drifts further and further from the true physical angle until the magnetic field vectors misalign completely, resulting in a total loss of torque.
So the backup parachute essentially just dissolves midair.
That's a great way to put it, yeah.
And that brings us to the final software failure mode, which is arguably the most dangerous: software overdefense and uncontrolled generation, or UCG. This is where the control architecture's reaction to an anomaly is significantly more destructive than the anomaly itself.
The software state machine has to be incredibly robust. Let's return to that bit flip scenario we talked about.
The cosmic ray.
Right. A noise transient or an alpha particle causes a single corrupted angle reading. If the software lacks proper debouncing logic, meaning it fails to wait for 2 or 3 consecutive clock cycles to verify the error is persistent, it immediately triggers a fatal fault response.
The processor panics. It instantly commands a safe torque off, an STO, aggressively clamping all pulse width modulation to the inverter.
And if the vehicle is pulling, like 1 g of lateral acceleration through a high-speed curve, an instantaneous loss of torque will violently shift the weight distribution,
potentially sending the vehicle into an uncontrollable spin on the highway.
Exactly. The defense mechanism causes the physical hazard.
It's like the car has an autoimmune disease. The defense mechanism is what kills it. But uncontrolled generation is the true hardware killer here, right?
It absolutely is. In field-oriented control, or FOC, the algorithm mathematically transforms the 3-phase currents into a flux-producing vector, the daxis, and the torque-producing vector, the coaxis.
Okay, so if the angle estimation suddenly skips 180 degrees due to a severe resolver glitch, the FOC algorithm's reference frame is entirely inverted.
It fundamentally believes the rotor is facing the exact opposite direction. So it mathematically reverses the coaxis current.
Instead of applying positive thrust, the inverter commands maximum negative torque.
And because the vehicle possesses immense forward kinetic energy, the motor is forcibly back-driven. It transitions instantly from a motor into a massive, unregulated generator.
It's aggressively pumping kinetic energy back into the high-voltage DC bus.
Yeah, and if the software's hard-coded panic response is to execute a 3-phase freewheeling shutdown, meaning it just opens all the high-voltage switches to protect itself.
That generated current has nowhere to flow, except right through the anti-parallel diodes of the Silink MOSFETs, straight into the DC link capacitor.
And the bus voltage skyrockets exponentially. It goes from 800 volts to over 1200 volts in milliseconds.
And once that voltage exceeds the avalanche breakdown threshold of the silicon carbide semiconductor lattice,
the PN junctions are completely destroyed. The modules literally vaporize.
the inverter is essentially a bomb that just detonated itself because it misread a single data point.
This is precisely why building an ASIL-D architecture is so incredibly complex. You are managing the physical mechanics, the electromagnetics, the quantum-level data integrity, and the software's psychological response to failure simultaneously.
Wow. Which transitions us perfectly into Section 4, building the ultimate shield. Because we've identified 16 horrifying ways this system can destroy itself, the materials outline a 6-dimensional defense grid deployed by engineering teams to immunize the architecture against these saboteurs.
Right. How do you build an immortal system?
Exactly. Let's start with dimensions 1 and 2, electrical, EMC, and timing parameters. How do they eliminate the parasitic pigtails and the floating oscillators?
Well, the defense grid mandates absolute 360-degree circumferential shielding for all sensitive data harnesses. The pigtail ground is explicitly banned in manufacturing.
Done away with completely.
Yeah. The braided metal shield must be terminated radially around the entire circumference of the connector shell, which creates a mathematically perfect Faraday cage.
So that minimizes the parasitic inductance to near zero, providing a massive low-impedance drain path for that 10,000-volt common mode noise.
Exactly. The shield actually acts as a shield.
Amazing. And for the temperature drift issue, the defense grid outlaws the barium titanate X7R capacitors in the analog front end entirely. The mandate requires Class 1 C0G, also known as NP0, ceramic capacitors.
Right, because C0G dielectrics use a calcium zirconate structure. They do not possess a piezoelectric or ferroelectric characteristic at all.
So their temperature coefficient of capacitance is virtually 0 parts per million per degree Celsius.
Exactly. Whether the inverter is freezing at -40 or baking at 150 degrees, the capacitance remains structurally locked. It ensures the differential resolver signal never drops below the comparator threshold.
Okay, so that solves the heat blindness. What about the metastability timing errors?
To fix that, they force the main MCU and the RDC processor to physically share a single high-precision crystal oscillator.
So they are hardwired to the exact same clock domain.
Yes, ensuring the setup and hold times can never ever slip out of phase.
And to combat the cosmic rays and alpha particles, Dimension 2 dictates that all SRAM and flash memory must deploy hardware-level ECC or error correction code.
Yep.
This utilizes Hamming code parity bits, correct?
Yes, it does. The hardware mathematical logic actively calculates parity bits for every byte of data. So when an alpha particle strikes the silicon and flips a bit,
The ECC hardware instantly detects the mathematical parity anomaly.
and it physically reverses the bit flip in real time within a single clock cycle before the motor control software is ever aware an upset even occurred.
It fixes the quantum error before the car even notices. That is incredible. Okay, moving to Dimension 3, algorithm and magnetic defenses. This focuses heavily on the software's predictive capabilities. The source highlights a Type IV phase-locked loop combined with a 2D lookup table to handle violent acceleration profiles.
Right, because a standard Type 2 PLL will exhibit a steady-state tracking error when the target is accelerating rapidly. In a dual-motor EV executing a launch, the angular acceleration, the jerk, is immense.
So a Type IV PLL utilizes 4 integrators in its open-loop transfer function, allowing it to dynamically track aggressive parabolic phase changes without lag.
Exactly. And furthermore, during those peak torque demands, the high current physically saturates the stator iron, which warps the magnetic flux linkage.
And that's where the 2D lookup table comes in. It maps out exactly how the magnetic field will distort at any given current and temperature.
Yes, allowing the software to mathematically precompensate the angle calculation before the hardware even experiences the distortion.
It is literal predictive phase compensation. And to fix the sensorless control divergence we discussed earlier, Dimension 3 implements an MRAS, a model reference adaptive system.
Which is basically giving the sliding mode observer a real-time thermometer.
I love that.
The MRAS utilizes Lyapunov stability criteria to constantly cross-reference the active voltage and current vectors, mathematically deriving the real-time temperature of the copper windings,
So it dynamically updates the stator resistance variable in the observer matrix.
ensuring the backup angle estimation remains perfectly synchronized with physical reality, regardless of the thermal load.
Okay, Dimension 4, sensor physics and sealing, brings us back to the mechanical defenses. To stop the EDM microlightning from blasting craters into the motor bearings, they integrate a carbon brush shaft grounding ring, or SGR.
It is such an elegantly simple tribological solution to a really complex electromagnetic problem. The highly conductive carbon filaments physically ride on the spinning motor shaft, providing a direct, ultra-low impedance path to the ground casing.
By continuously bleeding off the induced capacitive charge, the shaft voltage never reaches the dielectric breakdown threshold of the lubricating oil.
Right. The Townsend avalanche is entirely suppressed.
No plasma, no fluting. Brilliant. And to address environmental ingress, the entire sensor assembly is upgraded to IP69K sealing standards, which resists high-pressure hot water jets. But the most brilliant defense outlined in this section is perhaps the most primitive, the U-shaped drip loop.
Yes, because capillary action is incredibly powerful. Water will wick its way down the surface of a wire harness, bypass the seals, and pull directly onto the connector pins.
So the defense grid mandates the physical routing of the wire harness must dip down 50 millimeters into a U-shape before routing back up to the connector header.
So gravity mechanically defeats the capillary action.
I love that. Amidst all this talk of dynamic algorithms, active short circuits, and fighting cosmic rays, one of the primary defenses is just a U-shaped bend in the wire. Gravity pulls the water away. Sometimes the best engineering is just outsmarting nature with nature.
Absolutely. The water travels down the wire, collects at the lowest point of the loop, and drips harmlessly onto the under tray.
It really grounds you. No pun intended. Dimension 5 addresses the mechanical interconnects to prevent fretting wear and thermal runaway. They completely overhaul the metallurgy, moving away from standard brass alloys to beryllium bronze.
Beryllium bronze possesses vastly superior yield strength and spring relaxation properties at extreme temperatures.
This ensures the normal force clamping the pins together remains incredibly high, physically resisting that 100-micron vibrational sliding we talked about earlier.
And they pair this with a strictly enforced gold plating thickness greater than 1.27 microns to prevent any underlying oxidation.
And to act as a secondary barrier against oxygen and fretting, they mandate the automated injection of Niogel 760G anti-fretting grease.
The rheology of this specific synthetic hydrocarbon provides a hydrodynamic boundary layer. It physically dampens the microscopic shear forces while sealing the contact patch from atmospheric oxygen.
And to resolve the missing phosphate coating on the bus bars, the manufacturing line moves entirely to torque angle fastening strategies.
Because standard torque wrenches only measure frictional resistance.
Right. But a torque angle servo screwdriver measures the initial seating torque and then calculates the physical degrees of rotation to stretch the bolt precisely into its elastic yield zone.
This mathematically guarantees the target clamping force is achieved, driving the contact resistance below 20 millionths.
Completely neutralizing the risk of thermal runaway regardless of thread friction. That brings us to the final layer, Dimension 6, safety and extreme response. This dictates exactly how the software is allowed to behave when a catastrophic, unrecoverable error is verified.
Right. How do we stop the software from detonating the inverter with an uncontrolled generation event?
The defense grid strictly prohibits the three-phase freewheeling shutdown at high speeds, because opening the switches is a death sentence for the CT modules. Instead, the dual-core lockstep processor executes a precisely timed active short circuit, or ASC.
Shorting the phases together on purpose.
Yeah, and I read this section multiple times because, intuitively, shorting a high-voltage system sounds like blowing a massive fuse. How does shorting the phases prevent destruction?
It relies on the inherent physics of the motor's stator inductance. When the processor commands an ASC, it turns on all three high-side MOSFETs simultaneously, or all three low-side MOSFETs simultaneously, creating a zero-voltage vector.
It clamps the three motor terminals directly together.
Exactly. The motor is effectively severed from the DC bus capacitor. The back EMF generated by the spinning rotor now drives massive current, but that current circulates entirely within the closed loop of the stator windings and the MOSFETs.
Because the stator has significant inductance, the current cannot change instantaneously. The magnetic flux linkage traps the energy.
Yes, so the immense kinetic energy of the vehicle isn't dumped into the fragile DC capacitor to cause an avalanche breakdown. It is dissipated safely as I²R heat directly inside the massive copper mass of the stator windings.
The system voltage is clamped safely below 720 volts.
And critically, because the energy is being dissipated as heat, it produces a drag torque. The ASC mode smoothly ramps down the torque at a controlled deceleration rate of 500 newton-meters per second.
The vehicle doesn't violently lock its wheels or throw the driver into a spin. It gracefully degrades into a controlled limp state, allowing the driver to safely navigate to the shoulder.
It transitions a catastrophic hardware detonation into a controlled, safe deceleration.
Now, these 6 dimensions of defense, the beryllium pins, the Type IV PLLs, the torque angle algorithms, are magnificent for a pristine vehicle on a CAD screen.
Sure.
But Section 5 of the documentation asks the ultimate operational question. How do you manage this when there are already thousands of vehicles in the field and massive factories churning out hundreds of powertrains a shift? You enter the 8D framework.
The 8 disciplines of problem solving. This is the industrial standard for systemic risk management. When an ASLD hazard is detected through field telemetry, the engineering war room immediately executes D3, interim containment.
The absolute priority is to stop the bleeding and protect the fleet actively on the road. Because you can't recall 50,000 cars to change a pigtail ground in an hour, so how do you contain it?
You deploy a highly restrictive over-the-air, or OTA, software update. The OTA aggressively throttles the inverter's maximum switching parameters and limits the vehicle's top speed to a 40 km/h limp home mode.
By mathematically restricting the switching speed and the RPM, you physically prevent the system from generating the high-frequency parasitic noise and the massive back EMF spikes that trigger the hardware destruction.
It is a brute force containment strategy. It drastically reduces vehicle performance, but it provides a 100-mile safety buffer for the driver to get off the road without the inverter vaporizing.
Meanwhile, in the factory, the Manufacturing Execution System, the MES, instantly executes a digital lockdown. It cross-references the lot traceability database and physically quarantines any batch of microchips, wiring harnesses, or resolver assemblies associated with the anomaly.
And once containment is achieved, you move to D4, root cause analysis. And the document strictly mandates the use of the MECE principle here.
Mutually exclusive, collectively exhaustive.
MECE is critical when building a fault tree analysis. Engineers frequently conflate symptoms with root causes. MECE forces the team to isolate the variables. They must explicitly separate the symptom, the physical root cause, and the systemic testing escape point.
Okay, so if we look at the fretting wear example, the symptom logged by the processor is a signal degradation fault causing a stall. The physical root cause is that a 100-micron chassis vibration sheared the gold plating, oxidized the beryllium bronze, and induced a microarc.
Right. And the systemic testing escape point, the most critical realization of all, answers why the engineering validation team failed to predict it in the first place.
The 8D investigation might reveal that the component was never subjected to the specific LV214 SG4 extreme vibration severity profile during the design validation phase.
Exactly. You don't just fix the oxidized pin, you rewrite the corporate testing standards so that every pin designed for the next decade is subjected to the LV214 profile.
You update the DFMEA, the design failure mode and effects analysis, to permanently alter the engineering DNA of the company.
And you must equally update the PFMEA, the process failure mode and effects analysis on the factory floor, to eliminate human variance. Because human error is statistically incompatible with a 60-millisecond FTTI.
The manufacturing upgrades listed in the document reflect this perfectly. To ensure the wire harnesses are crimped perfectly, they introduce 360-degree automated servo presses equipped with force displacement monitoring.
The machine dynamically plots the force curve of every single crimp in real time. If the structural density of the copper strands is off by a fraction of a millimeter, the controller locks the station and rejects the part.
But the validation technique for the Niagel grease is genuinely brilliant.
Oh, the UV dye process. Applying clear synthetic grease deep inside a multi-pin connector cavity is virtually impossible for a human operator to verify visually.
So the process engineers mix a specialized UV fluorescent dye directly into the Niagel formulation at the chemical level.
It's invisible in standard factory lighting. But as the assembled wiring harness moves down the conveyor line, it enters an automated optical inspection, or AOI, station.
An AI-driven machine vision camera blasts the connector header with high-intensity ultraviolet blacklight.
And the AI isn't just looking for a glow. It evaluates the specific wavelength, geometric distribution, and volumetric intensity of the fluorescence to confirm that a mathematically perfect hydrodynamic boundary layer has been applied to every single pin.
If the AI detects a dry spot, the part is instantly quarantined. This UV dye process is fascinating. It feels like you aren't just designing a better motor, you're designing a system that entirely removes the possibility of a tired factory worker making a tiny mistake on a Friday afternoon, right?
You completely remove the fatigue of a factory worker from the ASIL-D safety equation. No human error allowed.
But what about the service technicians? The mechanics at the dealership diagnosing a stalled vehicle don't have access to acoustic microscopes or mass spectrometers.
That bridges to the final discipline of the AD process. The Central Engineering War Room must distill this entire 47-page masterclass of quantum physics, material science, and tribology into a simple one-page teardown checklist for the global service network.
It maps the physical inverter into a 5-zone diagnostic grid. The technician doesn't need to understand the Lyapunov stability of the MRAS algorithm.
No, the checklist simply states, inspect Zone 3 for carbonized thermoplastic ash, or verify the 50-millimeter structural dip of the U-shaped drip loop in Zone 4.
It translates advanced aerospace-level failure analysis into actionable, wrench-turning diagnostics, allowing frontline mechanics to rapidly trace a burned PCB or a scratched terminal back to the exact root cause without needing a PhD.
It ensures that the feedback loop from the service bay back to the design engineers remains pure and uncorrupted.
Wow. Bring the journey to a close here. We have traced this architecture from the subatomic impact of an alpha particle deep inside an SRAM cell through the electromagnetic violence of parasitic capacitance and microersing.
All the way to the deployment of predictive phase-locked loops, gravity-fed drip loops, OTA updates, and AI-driven UV grease inspections.
It fundamentally redefines the scope of automotive engineering. The transition from mechanical engineering to systems engineering means a modern car is basically a high-voltage supercomputer on wheels.
It really is. The integration density required for dual motor control demands that mechanical, electrical, and software domains are treated as a single, indivisible, cyber-physical entity.
And that leads to a profound realization about the future of this industry. A mechanical failure today isn't just a broken part, it's a massive data corruption event. A slight variance in the friction coefficient of a single bolt or a localized spike in atmospheric oxygen inside a plastic housing is a catastrophic event capable of violently destabilizing a vehicle at highway speeds in under 60 milliseconds.
It is entirely unforgiving.
As these dual-motor, hyper-complex architectures become the standard in our daily commutes to the grocery store, we have to ask, will the mechanics and technicians of tomorrow need degrees in quantum physics and cybersecurity just to diagnose a rough idle? Consider how the definition of fixing a car is changing forever.